today. So morning, welcome to this class for computer graphics today. You know it's a bit late, but there are things which you have to talk about today. And today I want to talk about starting on aspect of projections and transformations. I've uploaded the notes. Which you can use for reviewing all these aspects which you're going to talk about today. But the most important aspect which I'd like us to remember is that, as I've said in the label when I was actually in the meeting, the public charge, the welcome note which I usually have here on the right hand screen, and you open the note and you're opening it, you'll obviously find that I've said that these notes from today on, they shall be available on the YouTube platform. I will be recording. I'll be having pre-recorded classes, and then I upload on YouTube so that you can be able to access them. Because I remember last week you saw when you are doing the exam, there was an issue with the system whereby the system crashed because of the system memory, the capacity was overdue, and that was due to the aspect of the Big Blue video recordings, which are so many. So we have had to look for a way of ensuring that the capacity is scaled back to normal so that we can have efficient use of the system. Because if we keep on dumping all these recordings on the ZDS platform, then eventually the ZDF platform will be overwhelmed. That's one thing we do not want to do. So going henceforth from next week, there shall be pre-recorded videos or tutorials of me explaining the various concepts. Then I shall upload the link. So that you, my students, can be able to access the video from the YouTube side. Even today's video, I will still do the same for this pre-recording. So for those who will be looking for these pre-recordings, they will be all there on the YouTube. Even the ones which we had done earlier in the beginning of the month, that is in the month of May and June, I shall remove them from the ZDS platform, and then you shall be able to access them from the from the YouTube side. Sorry for that. So as of now, that is what I intend to do. As I see a lot of people are now starting to join the class. Welcome, those who are joining the class. Then by the end of the day, you shall have all your cut marks. I believe that is the thing which is now remaining. I know for some I've already marked. I don't know if I've marked for all of them. For some I've not yet marked, but it will be okay. So for this class, for this session, for the class today, it won't be that long. So welcome people to the class. Wale ambao wameingia sahi, tutaendelea. We'll look at these things. So this class today won't be long. I just want to explain the few concepts of projection and transformations. Projections and transformations, that's what we are looking at. And kindly take note that from next week, the classes shall be pre-recorded. I don't know if we shall have the capacity to do the online lecturing for the class, but I will be the live session, but I'll be pre-recording those videos, and I will be uploading them on YouTube so that you could be able to access them. So welcome to the class, people, once again. And we continue from where we stopped last time. And I believe you're able to see the notes for Bressenham and midpoint algorithm. I think it's important that you're actually aware of how those two algorithms work so that you can be at par. And you can be able to know how they work, and so that you can be at par with whatever it is that needs to be done. Those things. So welcome to this class. So for today's class, as I said, is about projection and transformations. And I'd like to start off with transformations. I'd like to talk about transformations. That's what we are starting off with today. And I would like to share my screen so that you can be able to see what it is that we are talking about. First of all, I believe you can all hear me. If you can hear me, you can just say it on the public chat. You can all hear me if my voice is audible. My voice is audible. I believe you can hear me. George Omondi, John Were. Thank you. Thank you, John. So let me share my screen so that we can get started off on this aspect of projections and transformation. So I've shared the notes as I said, so that's where we shall start off with the first thing. So 2D transformations. Here we shall be dealing with 2D transformations, two-dimensional transformations. Remember, I said in graphics that we do not have, as per se, 3D graphics. The current type of graphics we have right now is 2D. What most people talk about 3D is whereby you try and map 2D homogeneous coordinates onto a 3D planar area. So we do not have, as per se, that we have a graphic display or a graphic device that is 3D. Most of the graphic devices that we have are two-dimensional. Two-dimensional meaning that you can see it from the top and the bottom. That is what 2D is usually about. Now, with transformations, we have to look at why do we need transformations? What are 2D transformations? There's also another aspect to call homogeneous coordinates and combining transformations. Now, in graphics, transformation in a 2D planar space is an operation that alters the image parameters. So this is parameters story. There's an A here missing parameters. So that's what graphics is all about. That is what affine transformation is all about, whereby our work is purely wait a minute. The work is purely to alter the image of alter the image parameters. Now, in graphics, we're usually concerned with something we call the affine transformations. And affine transformations retain the ratio and parallelism of an image. That's what they usually do. They retain the ratio and parallelism of an image. There are three basic affine transformations. We have scaling, rotation, and translation. Those are the most basic ones: scaling, rotation, translation. Scaling is whereby you either alter the size, you either scale it up or down. Rotation is whereby you rotate it around a certain point of origin or around a certain coordinate. And translation basically means movement. That's what we have. So once you have an object described, let's say you have a triangle, you can perform these basic transformation to them, and we call them the affine transformations. Now, 2D affine transformations: translation, rotation. Translation basically means moving. Rotation, there's translation, and then there's rotation, whereby you rotate it as around a certain angle, around a certain point, and then we have scaling, you increase the size of the object. Now, translation basically means move an object from one position to another. That is what translation means. If I have a thing which I can be able to look at. Sorry, I have to do it like this. Something I'm looking for here. Notepad. Notepad. So sorry. So translation basically means movement of an object. And one thing we have to understand and get clear. Translation means movement of an object. So when you move an object, it basically means that you change the way that object behaves. So simply translation means moving an object from one position to another. And remember in graphics, I said that we depend on the coordinate system that is made up of X and Y. We have seen it even from the line drawing algorithms and everything. So if you're translating, it simply means that if you have an object here, you just basically move it. The new X coordinate shall be given by the old X coordinate by the change or the movement. Dx is the change movement in the X in the X coordinate, while dy is the change in movement in the Y coordinate. So we have to add them as per that. So translation basically means whatever it is that you have in your X axis, you add it to the translation movement and then you get your new point. It's basically when you're moving a car. And I believe you've looked at acceleration in mathematics. If you're moving a car from point A to B, what you have to do is just know what is the distance, what the distance from point A to B, how many meters or how many kilometers am I moving, and then you'll be able to get the distance that is needed. So translation example, for example, we have this kind of triangle. We have this kind of a triangle. And then you're told to translate it because that's how the thing will usually be. And you're told to translate it. So let me just have this. So we have given, can you remember that triangle? We have that triangle, the X and Y triangle. And then you're supposed to translate it. Just let me just share this thing to you guys here. Just a minute. Just a minute. There's something I want to do here. Upload it so that you can be able to. So let me just upload. Let me just try and upload that thing. I think it will be way easier if I upload it like that. I'm trying to upload the presentation onto the big blue button instead of keeping on switching and moving it all the time. So I want to upload it. Okay, converting. So it is converting the file to PDF. First of all, let it finish converting. So as you continue, so meaning that we have these coordinates. Meaning we have those coordinates. Taking a bit of time to convert. Let's continue. Meaning we have these coordinates. So if I want to move, let's say this image, I want to move the image. If there's somewhere I can be able to insert. Insert shapes. So let's say I want to move the image. Move the triangle by the following parameters. That is X, I move it by 3. Y, I move it by 2. So basically, you'll always be given, these are what we call translation coordinates. I move X by 3 and then I move Y by 2. So meaning that point A, so if we come to coordinate A, Coordinate A is made up of 1, 1. So the new A new, if I call the new A new where it shall be, if I move it by x is 3, then it means that I'll have to take 1 plus 3, which will give me 4. And then I'll have to take 1 plus 2, which will give me 3. That will be the new coordinate of A. For B, which is 3, 1, the new B will be given by 3 plus 3, which is 6, and 1 plus 2, which is 3. That will be the new coordinate of B. While C is the top one, it is given by 2, 3. The new coordinate, C new, shall be given by 2 plus 3 is 5, and 3 plus 2 is 5, and 3 plus 2 is 5. Remember by 5, 5, 2, 3. 3 plus 2x is 3, y is 2. Yeah, shall be given by that. So those shall be the new coordinates of what we are dealing with. So as you can see, when you move the triangle by x is 3 and y is 2, you shall have that kind of a scenario. Whereby it will be 5, 5, it will be somewhere here. So we shall have 5, 5, and then we shall have 4, 3, and then, so you see 5, 5 shall be here, 5, 5, and then we shall have the next one shall be 4, 3. So 5, 5, and then we come to 4, 3, and then from 4, 3 we come to 6, 3. So, and then shall be there. So the triangle shall have moved vertically upward. So translation basically is the simplest of all, whereby you just ensure that you do what? That you what do you call this? We ensure that you the thing is that you just move the triangle. So this is how. Remember I said that with translation you just add. You just take the x all plus the change, the translation. So you see it moves up. You can either move up or you can move down, depending on the translation coordinates you've been given. So if you was to do this, this is how I'll move the triangle. From A all the way there. A, if I add, A is 1, 1. Here is A. So if I'm moving this point A and I'm moving it according to x is 3 and y is 2, then it means that I'll have to add 3 to x and 2 to 1 so that I can get the new A. B is 3, 1. Which one is here? So if I add this translation coordinates, x, which is 3, 3 plus 3 will give me 6, and then 1 plus 2 will give me 3. And then C, which is 2, 3, which is here. If I add 3 to 2, it will give me 5. And then if I add 3 to 2, again, it will give me 5. So that will be the new C. So that's how you do the movement or the translation. You just add. Whatever it is in the old, you add it to the new. The new, you get it by adding the old to the change in X. So translation is usually the easiest of all aspects that can be that can be undertaken in in transformations. The other one which I want to talk about is scaling. Now scaling is somehow different. Scaling involves multiplying the object coordinates by a scalar element. Scalar element basically means like you have a scaling ratio. You either, if I was to multiply it by 3, you multiply it by 3. If I was to multiply it by 2, I multiply it by 2. So objects grow and move. One thing with scaling looks like that. Objects grow and move. Now we have two types of scaling. We have uniform scaling, and we have, if I may insert an object here, we have uniform scaling. Uniform scaling is whereby the scaling parameter is uniform for both x and y coordinates. meaning that you can be told to scale it by a factor of 3. If you're told to scale it by a factor of 3, it means that you can scale it by 3 in both x and y. That is uniform scaling. While non-uniform scaling is where we have different scaling factors in both x and y. For example, you can be told to scale x by 2, scale x by 2, and scale y by 3. So that is non-uniform. That is where the back stops with those two. Meaning, now in uniform, you will scale it using the same parameters in both x and y. In a uniform, it means that x will be scaled by 2 and y will be scaled by 3. Those are the two types of scaling we have. So for example, if we look at an example of scaling, uniform scaling, this is what it means. Scaling by a factor of 2, meaning that both x and y will be scaled by 2, while non-uniform means that you scale x by 2 or y by 0.5. So that is non-uniform, different scalar per component. Uniform, same scalar measurement in all the coordinates. Non-uniform is where scaling differs per component. That's what we have. Okay. So for example, let's say we have this parameter here, and we want to draw it by using by scaling it. So let's start first of all with scaling by uniform. Scaling by uniform parameter. Scaling by uniform parameter. Meaning, like, let's say, let's scale by 2. Let's scale by a factor of 2. Then it will ultimately mean that we have to multiply each of these coordinates by 2. So meaning that, like in A, our first coordinate is 1, 1 here. I believe you're able to see. This is my first coordinate. If I may call it, let me just try and input this one here. That is A. This point here is B. And this point here is C. So for those who might be asking, Mwalimu, where are you getting these things from? So let me just be where this thing has hanged. Just a minute. Close. So my system has hanged a bit. Sorry. Let me try and get it back. So I was doing like that scaling. Okay, that's translation. Oh, yeah, so imerudi scaling. Is that scaling? Yeah. So if I was to give those coordinates, it's back. This one will be C. So we have those points. So A is 1, 1. So my new A new shall be given by each of these coordinates 1 times 2, 1 times 2. So it will be given by 2, 2. That will be my new coordinate. B, which is made up of 3, 1. Yeah, I believe that's 3, 1. So that you can see clearly. 3B is 3, 1. So if I multiply it by a scalar factor of 2, then it means that by me, B new shall be given by 6 while my C is 2, 3. Meaning that new C, Modesty, kindly mute your mic. So my new C, trying to show you this thing aspect of scaling, uniform scaling. My new C now shall be given by multiplying these aspects by 2. So it will be 4. 2 times 3 is 6. So that will be my new C. So if I was to come and plot, meaning that if I was to come and plot, now I'll have to come and check here. 2, 2, where is 2, 2? So 2, 2 is, we may have something to plot here. 2, 2 is there, and then there's 6, 2. So meaning that, where's 2, 2? 2, 2 is here, and then where's 6, 2? So when I'm drawing up to there, so let me just increase the shape outline of this object. Increase again there. So now you see A new, B new. So basically this is, let me just write AN, and this is BN. It is AN, and this is BN. AN and BN. So that is AN, which is 2, 2, and BN, B new is 6, 2. And then C is 4, 6. 4, 6 iko wapi? 4, 6 iko hapa katikati. So iko hapa.
Excuse me, sir. Sorry for interruption, yeah. But I can't see the demonstration.
You can't see the demonstration? Oh, sorry. Let me share. Okay. Okay, sorry about that. So as I was saying, we are scaling. Let me just go back from the top. We are scaling. Let me just move these things from here. Okay. Just to remove these things. Let me just remove these things. I want to have the original things. Now, this is the original triangle, and we are told to scale it by a uniform factor of 2. Remember, I said that scaling, we have 2 types of scaling. We have uniform scaling, which means that the scalar parameter is uniform for both x and y. And then we have non-uniform. Non-uniform meaning that x and y are different, meaning that I can scale x by 2 and y by 0.5. So that is non-uniform. So scaling, we said, is purely when you're doing what? Scaling is when you're increasing the size of your object, and scaling involves both objects growing and moving. And the way we get scaling, scale is by when you take the current coordinate you're having, multiplying it by the given scalar factor. That's one thing we have to agree with scaling. It involves those 2. Meaning that if it involves these 2, it means that scaling, there are 2 types of scaling. We have uniform scaling, which I said is whereby the scaling parameter is uniform for both the x and y coordinates. And then you have non-uniform, whereby x and y have different scaling factors. So uniform scaling is whereby I say that if you're told to scale this image by 2, it means that everything here, be it x and y, will be scaled by 2. It will be increased by 2. It will be multiplied by 2. If it's non-uniform, then it means that each scalar factor in the coordinate, be it x and y, shall be scaled by an individual parameter. Like, for example, here we are saying that we scale x by 2 and y by 0.5. And then here we have our scaling matrix, how we can be able to get the scaling matrix. I'll share this book with you. There's another book which I have which talks in depthly about this scaling matrix, how we can be able to formulate it. And then I came to this example which you're having here. And the first example I wanted to show you is how do we scale an image or an object using uniform parameters. That is when you have the same scaling ratio. And I was giving you this example. We have this, our original image, which is given by these coordinates, A, B, and C. And then we wanted to get our new image. Now, our new image, we are saying we scale it by a factor of 2. So if it's scaling by a factor of 2, then it means that this scaling factor is uniform. So if it's uniform, then it means that that we multiply each aspect in these coordinates by 2. I hope you remember that. With uniform scaling, if it's uniform scaling and you're just taught to scale by 2, it means that all the coordinates you have in your image, in your original image, you'll have to multiply it by 2 to get the consecutive or the consequent image that will be the new image. And that's why I came here. I took 1, 1, multiplied by 2, I got 2, 2. And then I had 3, 1, which is here, and then I multiplied by 2, I got 6, 2. And then I had 2, 3, which is here, multiplied by 2, then I got 4, 6. So using that, meaning that if I was to draw this new image, it would come to this. So it would be 2, 2 and 6, 2. So to start from there, that would be the new image. And that's why I came here and I say that AN basically stands for NU. If I just put it like this, AN, and you have BN, and then you have CN. Basically, it means C new. It's basically a new coordination point. It's just a new coordination point. That's why I had it there. AN is here. Then BN is here. 6, 2. You see 2, 2, 6, 2. Now, C now would be 4, 6. 4 is here. So it will be there. Meaning that if I was to draw it then, it would mean that it would be 4, 6. So I would have a line joining from here to here. Then I would have another line. Thing is hanging a bit. Let it just malize kuhang, and then because I'm editing a live presentation, so there's a thing which is going on. Let it finish hanging. Oh, but I believe you're getting the drift of how this scaling will be. Sorry. So it will be here. And then the other one, because 4, 6, it will be all the way here. So you have to join those coordinates. So meaning that this would be our new image. Now you see, now this is C new. C N. Now you see our image has moved from this one which you are here, which you are having here, to this one which you are having here. So that is uniform scaling. That is uniform scaling. Now, non-uniform scaling, if I just do it here, non-uniform scaling, I want you to see if maybe I can just change the color. Let me just change the color of this. No, I want to change the color. Yeah, wait. Let me change the color. Yeah, red. So this one for red is uniform. Red is uniform. Let's just put it there. Red is uniform. So red is uniform. That is uniform scaling. That is a triangle of uniform scaling. Now, non-uniform scaling, I believe we can still see it together. Okay, non-uniform scaling now. Uniform scaling is whereby if you have different scaling parameters, let's say we are told, let's say to scale x by 2. So we scale x by 2 and y by, let's say we scale y by 0.5. So how will it be now, the new scaling parameter? So we have our a. A is still 1, 1. So our A naught, our A1, if I could call it like that, our A1 would be 1 times 2 is 2. 0.5 times 2 is 1. I believe you all know that. 0.5 times 2 is 1. So that will be the new coordinate for A1. B, which is 3, 1. Our new B shall be given by 3 times 2 is 6. 0.5 times 1 is 0.5. And then C, our C is 2, 3. If it's 2, 3, meaning that wait a minute. 1 times 0.5. What is 1 times 0.5? Just a minute. 1 times 0.5 gives us 0.52. Now, okay, sawa. I was doing it incorrect. So C1 shall be given by 2 times 2, which is 4. And then 3 times 2, 3 times 0.5, which is 1.5. I believe we have seen that. As in A is given by 2, scale A by 2, scale X by 2, and Y by 0.5. So it will be 2 times 2 times 1, which is 2. And then, 1 times 0.5 is not 1. It is 0.5. Sorry. That was where the whole mistake was. It is 0.5. Sorry. Yeah, I was going to show your calculation in end up here. If you do 1 times 2 is 2. 1 times 0.5 is 0.5. I believe that is now okay. Now, let us scale it now. We come here and we draw it. Let's draw that diagram. We see how it looks like. So the way we shall draw it will be, so 0.5 shall be somewhere here. So it will be 2, x is 2, 0.5. So x is 2, 0.5, and then the other one is 6, 0.5. So if we draw a straight line, it will be there. So let's color this green, and we give it a very weight there. And then we have, that is 2, 0.5 and 6, 0.5. And then we have 4, 1.5. So 1.5 is around here. So if 1.5 is around here, so then it means it's up to somewhere there. And then the other one is from there up to here. So we give it weight, green. We give it weight, green. Give it weight, green. Now, so this one will be C1 if we just insert it here. Okay, let me just change this one. We do it like that. The original ones, we do it like that. And then the new ones, new ones to yache to blue, light blue. light blue. And then the C1s, the new ones now, the C1, let me put it in form of a circle, C1. A1, actually this is A1. A1, B1, and this one is C1. So here, let's mimic the color that we have chosen, blue, no green. Just a bit green. And then green. So I believe you've been able to see uniform scaling. So blue represents the original triangle. Blue is the original triangle. Red is the uniform scaled triangle. And green is the non-uniform scaled triangle. I believe we have been able to clearly show what those two actually are all about. Just a minute. Sorry about that. Now, class, I just have a question. I hope you have understood. I hope you have understood the modalities of this scaling. This scaling. I've talked about scaling, and I've talked about. I never did it for translation, but if I was to do for translation, I want to ask for scaling, Mwanzo, scaling. The way I've shown, the blue is the original triangle, red is the uniformed scale triangle, and green is the non-uniform scale triangle. And that is how we get the non-uniform, whereby if the original is 1, 1, and you're taught to scale by x is 2 and y is 0.5, then we have to multiply each of them by those given coordinates. If it's uniform, then it means that we multiply it by that scalar factor, which is the same. I believe we are together on that. We are at par. We are at par on that. I believe we are at par on that. Now, if you may allow me to go back to translation. Translation, I never knew that. I never drew the triangle. Sorry about that. And translation, we basically said is moving. We are moving. Basically, you are moving. You are moving the triangle. And if I was to draw it, if I was to draw that triangle, if I was to depict it, where are the shapes? Yeah, it was to depict it. The first one was 4, 3, and the other one was 6, 3. 4363. So it will be like that one up to there. So let's get this purple. We give it more weight that it can be actually be depicted there. And then the other one is 55. So 55 equal upper. So we still draw it 55. So there, and then here. So if I just do the shape effect, the weight, that one, the shape effect, the weight, that one. Now that is that one will be our translated image. This is the original. This is the translated. You see, translation basically moves, but it just keeps the shape. The size is still the same. Translation, you just do the addition of the parameters. Where I was saying, if you're told to translate by x is 3 and y is 2, you just come simply here, you add 3 plus 1 and 2 plus 1. You get 4, 3. 3 plus 3, 6. 2 plus 1, 3. 3 plus 2, 5. 2 plus 3, 5. That's how you get the new coordinates. That's translation. Translation is very simple. Scaling now, on the other hand, it's a bit different. That's what I was trying to show with scaling. With scaling now, this is how it will be. You'll have the original point. When you scale it, uniform scaling, it will be big. Now, non-uniform, you see it's a bit stretched towards the side and it's a bit compressed. Any question on those two aspects, if I may ask? Any question? Any question? Any question? Believe you can see the demonstration. Any question? If you have a question, you can unmute your mic and ask before I proceed to rotation. Any question, my dear students? Okay, it seems there is no question. Okay, there's no question. Good. We continue. Now we come to 2D rotation. Now, rotation is now where there's a lot of work. And rotation, I believe, we have to remind ourselves of a formula which you used to have when you are looking at the coordinate system of an object. When you're looking at rotation and translation, using the coordinates, using the cosine and sine calculations which you used in high school. So rotate all coordinates by a specified angle is given by this formula, whereby the x new is whereby you take your x, the old x, times cos theta minus y old times sine theta, and y new is given by x old times sine theta plus y old times cos theta. That is how you get your x coordinate. I believe that you should remember that formula with abandon. You should always remember that. This now, this handout explains about the 2D translation, how we are able to get that something we call the trigonometric identity. Yes, Cleophas. Any question?
No.
No.
Yes.
Hello, Cleophas. Is there any question?
No.
Okay, then mute your mic kindly. So, where was I? Now, as I was saying, this 2D rotation, two-dimensional. Remember, it's two-dimensional. We just see the top and the bottom, the side only. This 2D transformation relies on something we call the trigonometric identity. Relies on the trigonometric identity. This trigonometric identity, I remember, I know that you must have encountered it in high school. I won't have to go through those basic modalities of that trigonometric identity aspect of it. The only thing which I would like us to be quite certain is the formula. This formula, it's really important for you to remember that formula. It should be, translation, it should be like it's like your Bible. You should remember it. And it's gotten from the trigonometric identity. So that formula, we shall be using it so much when you're looking at rotation. So 2D rotation. So one thing with 2D rotation, you must have been given a point with which to rotate. Okay, you must be given a point with which to rotate a certain angle, to rotate that aspect around a certain angle, around the origin. Remember, we are rotating it around the origin. Okay, we are rotating it around the origin. So if you're rotating it around the origin, so let's say we have this image that we're having here, and we want to rotate it around 45 degrees. So rotate the image. Rotate the image around 5 degrees. How do we go about it? Now, this one will entail us doing a lot of calculations. And one thing I would like to remind you is that you should always be having what we call a scientific calculator with you. Scientific calculator. So basically meaning that A, nu shall be given by x is 3 times cos 45 minus y is 1 times sine 1 times sine 45. This is how we get for A, that will be the x coordinate and y coordinate. So you have to do it for both x and y. So this is ax. Now, a1y, the y coordinate shall be given by x, which is 3, sine 45, plus y, which is 1, cos 45. So you'll have to do for both. So b1x given by 5 cos 45 minus 1 sine 45. And then b1y, the y coordinate now, will be given by x, which is 5 sine 45 plus 1 cos 45. And then C, the new C1, the new C1 x coordinate shall be given by 4 times cos 45 minus 3 times sine 45. There's something, the machine, I think it's hung a bit. Let it finish, he's trying to write that formula down. So remember, as you can see, that for the new coordinate, you have to do it for x and y. If it's A, you have to do for both x and y. B, you have to do it for both x and y. And C, you have to do it for both x and y. So 3y sine 45 here. And then C1y is given by x is 4 sine 45 plus 3 times cos 45. So how do we get this? So let me just go to my calculator here. Always good to have a calculator.
Excuse me, sir.
Calculator. Yeah.
I can't see the screen.
Yeah. You can't
What
see the
you're
screen.
demonstrating? Yes.
Okay. Okay. And you can't see the demonstration. Well, I thought it was viewable. And now, is it viewable now?
Not yet.
Not yet. Let me just stop it and then we'll try again. Let me just stop it.
Okay.
Okay, there's something. I think there's something. Hide presentation. Okay, just a minute, just a bit. Now, is it visible? Is it visible?
Yes.
Okay, so I think I think there's a problem with the network. That's why sometimes it's connecting and sometimes not connecting. Okay, now let me just start off from the top. We are talking about rotation, and rotation, I said we rotate it around a certain angle about the x-axis, around the origin. That is, the origin is 0, 0. So meaning that this is the formula for calculating rotation. And it's really important that you remember this calculation. So meaning this calculation is gotten from something we call the trigonometric identity. This is the trigonometric identity which we are using. So this trigonometric identity is the one which you shall be using. Trigonometric identity is the one which shall be using to calculate the rotation of this object. And this is the trigonometric identity for which to calculate the rotation of an object in a 2D display. So with this trigonometric identity, it means that now, if you are to rotate the image around 45 degrees, it means that for each of these points, if we still remember I had given these aspects as this was point A, this was point A, no, wait a minute, that was point A, and we have point B, and you have point C. Remember, that's the point of our triangle. And we are trying to rotate this triangle about 45 degrees above the origin. That's the example which I wanted us to look at. We are trying to rotate it around the origin. So if you are trying to rotate it around the origin, then it means that if it's around 45 degrees, so if it's around 45 degrees, then our triangle should come around this joint here, around here. So what it means is that when you're doing the rotation, it means that for each coordinate, you have to find the subsequent x and y coordinate of the new coordinate. Meaning that if it's A, our new A, we shall have to get the x and the y. B, our new B, we shall have to get the x and the y, new x and y. And C, you have to get the new x and y. Are we together up to there, my dear students? I believe we are together up to there. So if we are together up to there, then it means that it means that it's there. Then it means that with these new aspects, then it means that our new coordinates shall have to be gotten by this. And that's why I say that for us to calculate this 2D rotation, then it's a matter that we must have our calculator. And where's the scientific calculator? Must have that scientific calculator, trigonometric function. So our first aspect is whereby we have 3 cos. What is cos? First of all, you have to ask yourself, What is cos 45? Let me just check. See. What is 45 cos? It is 0.0700. So we have to remember that. Cos 45 is 0.7071. Sin 45, what is about sin 5? It's still the same, 0.0701. So basically meaning that for us here, if you are to remember that, now we are remember the first thing you have to do when you're calculating this thing, we have to remind ourselves what is sin 45, not is cos 45. So sin 45 is equals to 0.7071. Cos 45 equals to 0.7071. That is one thing we have to remember. We have to remember ourselves. So, meaning that for us to get this calculation, then it means that here we have to come and do let me do for the first one. Meaning that it will be 3 times 0.7071, 2.2, that will be 2.1213 minus, what is 1 times minus 1 times 0.7071? It will give us 1.142. So here, our first coordinate for x will be equal to 1.4142. Now, what about y? Our new y shall be given by 3 times 0.7071, which is the same 2.123 plus 1 times 0.7071. This will give us 2.8. 2.8284. 2.8284. Yeah. We have done for A. Are we together up to there, my dear students? Are we together? Although this thing is hanging, let it finish hanging a bit. It's hanging a bit. Okay. Now, are we together? The first coordinate, the way I've been able to get for A. A now meaning that our new A, the L will be 1.4142, and our new B, our new Y shall be 2.8284. That is how we get now that Russian image. So it means it will be around this region. It will be around this region, meaning that A will be around 1, X will be around 1.4 something, B we shall be around 2.8. So it will be around this place here. Be around this place. Now, let us come to the second one. Let's come to the second one. 5 cos 1 theta. So it will be 5. So this one again shall be 5 times 0.7071, which is 3.53, minus 1 times 0.7071, which shall give us 2.8284. And then B shall be given by by shall be given 5 times 0.071. Done here. 5 times 0.701 minus, plus, not minus, plus 1 times 0.7071, which will give us 4.2. 4.246, 4.2426. That will be B. And then C, will be given by 4 times, 4 times 0.701 minus 3 times 0.7071. Let me just a minute. It is 4 times 0.4 times 0.7071. 4 times 0.7071 will be 2.8284. And then what is 3 times 0.7071? 2.13. 2.1213. Sorry, I just have to get these mathematics correct. So it will be 2.8284. 2.284. 2.8284 minus 2.1213. Oh yeah, so it will, this one will be 0.7071. Then this one shall be given by 4 times 945 is 0.7071 plus 3 times 0.7071, which will give us around roughly 4.9. Will give us 4.947. So that is how we get those coordinates. Now, if you come to plot them here, then it means that the first one will be 1.14, around, let's say somewhere here, and then 1.14, and then 2.8. So it will be around here. And then the other one will be x will be 2.8. Let me just star. So it will be 1.41, and then 2.8, and then 2.8. So around here, around there. And then the other one will be 2.8, which will be x, 2.8, and then 4.26, 2.8, then 4.26. 2.8 around here, then 4.26. Somewhere, let's say if I was to put it, 2.8 is around there. Let me just put it there. And then the other one will be 0.7. 0.7. 0.7 is around here. And then 4.9 should be around. Then 4.9 should be around there. 0.7, then 4.9. 0.7. Let's say it's around there somewhere. So if we are to join these lines, I believe we can be able to get the shape that we want there. First one. Then the second one. And then the third one. Now let us just shape effect yellow. And then the weight. Then the weight. Then that the last one. And there we have rotated our image. You see now, this is, if I was to show you how that thing has worked. If you are to look at the way we have rotated it, if you used to rotate it around this, around there, then this one else, we pass it around here. But to pass it around there, let's say we have that is black, then the weight. Then the weight, then the weight. Now, this angle here, let me just rotate it. Let me just try and rotate it. It's confusing to rotate. Bit. Hey, boss. Stop hanging. Stop hanging a bit. Stop hanging. Yeah. Oh, no. No. That angle here is 45 degrees. This angle here is about 45 degrees. That's the angle, about 45 degrees. So that is how we do rotation around the point of origin around 45 degrees. Now, any question up to there? We have covered translation, rotation, and and scaling. Any question? Any question? Any question? Just a minute. I have to receive a call. Just a minute. Okay. That was about the 2D rotation and 2D rotation. Yeah, that's about 2D rotation. Basically, that is where I'm supposed to reach up to there, but there's a handout which I'll give. It will also encapsulate shear and reflection, which I believe it will be up to there. But the most important one is to understand the three basic one. That is translation, how to do translation, and how to perform scale, and how to perform rotation. Those are the most important one, which you're supposed to understand and know. Now, before I introduce the aspect of projections, any question before I introduce the aspect of projection? It should take us 10 minutes. Many can call it a day, so that I can be able to finalize with your cards and everything. Any question about what you have looked at? If in case you have anything, you can always refer to me. Any question? Dear students, any question? People, Cleophas, Dixon, John Were, Wanjiku. Any question? Ama mmelala? Mnasikiza hii class mkiwa in the comfort of your bed, mmelala, mmejifunika blanket. I hope that's not the case. I hope that's not the case, dear students.
No, for me, I'm good.
Okay.
No question.
Dixon. Yeah?
No question.
No question. Yes. Okay. John, where? John. Okay, Wanjiku.
Yeah, I wanted to ask something, but not related to today's class. Did we get a go ask. To continue with the research paper?
Okay, I will give the go ahead by the end of the day.
Okay.
I'll look at them and then I'll give the go ahead by the end of the day. Thanks for that. Sasa. Is that okay, Wanjiku?
Yeah, very okay.
Okay, sawa. So let us finalize on projections. Let us finalize on projections. Slide. So projections and we have covered transformations, basically the three of them. Now we have to look at what is projections. And the goal is to understand the different kinds of projections we are having. So projection is basically, even before we talk about projections, it's purely having a line of sight towards an object. Like the way, if you are in a physical class, I would have come to class with a projector so that I could be able to scale and even move and even rotate the images that are saved in my PowerPoint presentation so that you students could be able to view. So here we're looking at projections, and projections purely around the three transformations which I've talked about: the scaling, the rotation, and the translation. So projections and scaling go about. Projection, if you was to define projection, so projection is basically a transformation. So we have to define a transformation from the 3D space to the 2D space of the display device. That is projection. So meaning that in all our presentations that we are having, they're mostly modeled around the 3D space. Now, how are we able to model that object from the 3D space to the 2D display device that we're having? That is what is called projection. So you project. And remember, we say that it's displaying a 3D image onto a 2D display. For example, our monitors, I think our monitors are purely around 2D. Projectors even 2D. But when you are transferring that projection from our machine. It might be in a 3D space. It can be viewed in a 3D space. So then how are you able to devise it from the 3D space to the 2D surface of the display? The transformation is called a projection. So that is what projection is all about. So we're usually projecting a 3D object onto a 2D surface. So first thing you have to do is select the projection surface and then defining projectors or line which are passed through each vertex of the object. So this is an example. This is our viewpoint. This is the projector line. This is the projection, and this is our 3D object. So plane of projection, and then you have the projection of this parameter. This is our projection point, which shall have to be displayed here, and this is our viewpoint. So projection basically enables us to view 3D objects onto 2D planes. Now, the most common and simplest projections for viewing 3D scenes are usually called planar geometric projection. Okay, so we have the first type, the simplest form is what we call planar. So planar is whereby projections are basically based on straight lines for projection. For example, this is a planar because it's based on a plane. So it's a planar based on a viewpoint. So you'll have a straight line connection on what is displayed to your 3D object. So this is what you see. You'll see the object here, but the object is actually behind here. Okay, so that's the first one. You have the planar geometric projection. Okay, we have the planar geometric projection. And this planar geometric projection, they come in two forms. You have parallel and you have perspective. Okay, you have planar geometric projections, and these come with two of them. We have parallel, use parallel projectors, and perspective.
Excuse me,
Perspective
sir.
projections which use projectors which pass through one single point. Yeah. Screen. Screen
yeah.
tena.
Yeah.
Ama?
And screen.
Okay. Okay, let me just sort it out a bit. I think there's a problem with this thing. There's a problem. I think there's a problem. There's a problem. I don't know if it will be sorted. The presentation. Let me just try and upload this presentation. We see if we can be able to view it. Okay. I believe. Check. Let me try and share it again. Just give me a few minutes. Try and share this. Okay, there's something totally okay. Okay. Now, can you see the slides? Lesson 7, where we're talking about projections.
I can see it now.
Sawa. Okay, because the screen has an issue, so meleta shida. I was talking about the two common classes of planner. Planner is basically whereby you view it in a straight line. That's what you mean planner. You view it in a straight line, kind of a projection, and it's usually the best. The one which was saying that you have a plane of projection, and then each point of the object, of the real object, the 3D object, is mapped directly onto the plane of projection in a straight line. That's what we call planar projection. And in planar projection, you have two types. Okay, straight lines. As I said, planar use straight lines for projections. That's what the most common which we use. There are two types of planar. We have parallel, which use parallel projectors, and you have perspective, use projectors which pass through one single point called the view point. Now, most projectors that we're having are called the perspective projectors. Because if you look at the projector, we have like a small camera, a small circle aspect at the front, whereby all aspects of that are passed through that single point called the view point. So most projectors that we are having today, they are the form of perspective projections. Now, parallel projections are also called orthographic projections, and they usually have this aspect of mapping, and we usually use vectors, and vectors are categorized by these projections. And we say that this vector of D passes through the vertex V, may be expressed in the form of a parametric line equation of V, which is the vertex plus the change in D. So, but these calculations are not that important. I never usually test them. The only thing which I wanted you to be aware of is the type of projections we have, and why projections and transformations usually come hand in hand. Because with projections, you can either scale or even rotate about an image that we are having. Now, that's what we talked about, perspective projections, whereby, like, for example, the normal projectors that we're having, those are perspective projections, and all rays pass through one point in space, the center of projection. Then, if the center of the projection is behind the plane of projection, then the orientation of the image is the same. By contrast, in a pinhole, it's inverted. Okay, normal cameras are usually inverted. That's one thing you have to understand and appreciate. But for projectors, it means that all the light has to go through that one area, the viewpoint. And that viewpoint is something that is really important because it's a perspective projection. And you have to appreciate that it usually occurs because of having a single point in that aspect. Though for projections, there's nothing much. I just wanted us to know there are those two. There's planar projection, whereby we view 3D objects onto 2D surfaces using a straight line. And there are two types of them, usually perspective and parallel. Perspective projections are ones whereby we use where the normal projectors are in use at the moment. So for today, I believe that I have tried to cover as much as possible what you wanted to cover today, so that next week I will be uploading the aspects of clipping, unless there is a question which you guys would like to ask. Any question? Unless there is a question, I would like to end the class there today. Any question, people? Any
Yes,
question?
I have
And
a
then
question.
kindly remember that this video, yeah, ask.
Mine is about the attendance. Do you normally mark it? Because it doesn't reflect on my side.
I normally, okay, for the past like 2 weeks, we have not been having classes because of preparing for exams, but I normally mark it. Does not reflect
Okay.
it?
Yes.
I normally mark it, and we take 2 of them. We have the attendance for this big blue button, and then you have attendance now for those people who normally access the notes and everything. But it's normally there.
Okay.
Yeah, but for the last 2 weeks, I've not marked it because you have not. Remember, you guys, you had been given a break so that you could concentrate on your last semester's exams for revision.
Mine is showing that for like this month, the whole of this month has not been marked.
I will review it. Sasa, I'll check on it. Once even when I'm marking these cards, Sasa, I'll review it. Okay. Any other question? Any other question? Where Dungu Ishia?
For me, I'm good to go.
Yes, you're good to
I'm
go.
good to go.
So, and kindly remember, kindly remember that this presentation we had today, it will be available on YouTube. I'll just post the link once the video has finished converting. I'll post the link on the ZDS site because remember we said that even I think from next week I shall be doing pre-recorded videos so that which can easily be accessed on YouTube, so that there won't be an issue whereby we start having to we start burdening the system with saved videos, which eat up a lot of memory. Sawa. Okay. So you guys, wale ambao tunakutana BPM tutakutana, wale wengine we see each other next week. Believe that will be okay. So the notes are already on the platform, so we shall meet next week. Okay, so have a blessed week.